All right, so this chapter we're starting is on refrigeration and heat pump cycles. Some of it is a review from Thermo 1. So first of all, let's just cover a few things on review. First question is, what is a refrigeration ton? Sometimes it's abbreviated RT, or sometimes we'll say, what is a ton of refrigeration? Sometimes I've seen it abbreviated TR. I think this is the preferred RT, a refrigeration ton. So what is it? Is it a amount of cooling in BTUs or kilojoules? Or is it a rate of cooling in kilojoules per minute or BTUs per minute? Or is it a specific amount of cooling like kilojoules per kilogram or BTUs per pound mass? Or is it specific rate of cooling, kilojoules per kilogram minute or BTUs per pound minute? Or is it mass of cooling in kilograms per BTU or pound mass per BTU? I'm going to pause. I'm going to walk around. I'm going to look. Just write your letter answer down on a sheet of paper, please. It's a little warm-up exercise, isn't it? So it's a rate of cooling. It's B. So it's in either kilojoules per minute or BTUs per minute. It goes back to 2,000 pounds of water at 32 degrees F, saturated liquid, and you want to make it 32 degrees F saturated solid, and you want to do that in a 24-hour time period. That is the rate of cooling in order to accomplish that. It goes back to ice production. That's what it goes back to. So one refrigeration ton or ton of refrigeration is 200 BTUs per minute or 211 kilojoules per minute. So let's continue the review. Another question is a refrigeration cycle has a metric called the coefficient of performance. So as review, you think of having a system and you have a thermal reservoir and a thermal reservoir. By convention, we put the high temperature thermal reservoir on top and the low temperature thermal reservoir on the bottom. And a refrigeration cycle is to do what? To consume some sort of power, some sort of energy, mechanical energy. You could put W dot there, supplied into the system. And what does it do? It promotes the transfer of heat, Q dot, out of the low and into the high. For a refrigeration cycle, what is, first of all, the definition of the coefficient of performance? I'm going to walk around. I'm going to see if you can just write it down. What is the definition of the coefficient of performance in terms of Q dot H, W dot, Q dot L? All right, so this is one of those areas where a lot of you are remembering, oh, our textbook uses gamma. No, our textbook uses beta. True? Do you remember that? One of them is coefficient of performance for a heat pump. One of them is coefficient of performance for a refrigeration cycle. I prefer COP, coefficient of performance, with the subscript R for one of them and COP subscript HP for the other. Which one is for the refrigeration? Obviously the subscript R, and then HP for the heat pump. It's less confusing to me. Otherwise, I got to interpret what's gamma, what's beta, right? But I think some of you were saying that this beta in our textbook is COP of the heat pump, and gamma is COP, I'm sorry, of the refrigeration. Then gamma is COP of the heat pump. Anyway, there you go. So what I asked was what is the coefficient of performance of the refrigeration cycle in terms of these W dots and Q dots? Well, always think of this is what I want or what I have to pay for or what it costs me. So what do I want for the refrigeration system? I want to pull a lot of heat out of some low temperature. And then what do I have to pay for? Well, I've got to buy electricity. So there's a good definition. Some people jumped the gun and they said they said that W dot is equal to Q dot H minus Q dot L. Where did this come from? Is that true? Is this true or false? True or false? Is W dot equal to Q dot H minus Q dot L? Is true or false? True. And then, if it's true, how did you get it? First law for the whole system. That's right. So it's an energy balance for the whole system. You have two ins, one out. Two rates of transfer in, then out. Okay, that's a good review of the coefficient of performance. Now let's you answer this question, please. Is the COP always greater than 100% or 1? Is it always less than 100%? Is it always greater than 0? Or is it always between 0 and 1? So you give me your answer on what is the COP. All right, we're going to get to some refrigeration systems which are not really all that efficient. And that's later in the textbook, but they'll have low COPs. They may have a COP of 0.5, meaning that if I want 1 kilowatt of cooling, guess how many kilowatts of power I have to supply? 2 kilowatts, doesn't it? Which means I got to dump 3 kilowatts of heat to the environment somewhere. That's not a very efficient system, but yes, you can have it. What would be the COP for this one? 0.5? Yeah. Some of them are more like 3. 3 kilowatts of cooling I can get for 2 kilowatts of power in, which would mean I would have to dump 5 to the environment. True? Did I do the math right? All right, 3 plus 2, 5. Okay, so what would be the COP? 1.5. So armed with that information, which one is the best answer? C. It just has to be greater than 0. It can be, 0.2, 0.5, 0.8. Not very good. I'm not proud of those systems. Or up in the 1, 2, 3 range. Then, now we're doing good. All right, ready for another question or not really? You're not really. The Carnot Refrigeration cycle coefficient of performance analytically can be expressed as 1 minus TL over TH, or 1 minus TH over TL, or TH minus TL, all of that divided by TH, or TH minus TL divided by TL, or TH divided by TH minus TL, or whatever. Got them? One of those answers is correct. Which one? And I see a lot of people already in the equation sheet. So let's do this. What is this one? TL over TH. That's the Carnot efficiency for a heat engine, isn't it? Heat engine. So it looks nice, but it's not the right one. And then we can derive or reestablish it by taking this as the basic definition, using this as a conservation of energy statement. And some people even wrote COP refrigeration. First time I walked around, they said, oh, it's Q dot L divided by Q dot H minus Q dot L. I saw that. A few people wrote it from memory or whatever. Does that look right? Okay. And then they took this equation, they divided both numerator and denominator by Q dot L, so they had 1 minus Q dot H divided by Q dot L minus 1. True? And then they remembered all the way back to the introduction of entropy and reversible and Kelvin temperature scale, the absolute temperature scale, that if it's in completely reversible cycle, you can replace Q dot H divided by Q dot L by what? TH over TL minus 1 divided by 1. And then you just multiply both numerator and denominator by TL. And you finally get what we're interested in is TL divided by TH minus TL. How's that for a quick review of the Carnot, which is the maximum COP for a refrigeration cycle? You can express it in terms of absolute temperatures. So it was F, Very good. A lot of people had the correct answer. I may have told you F was wrong. Sorry if I did. Did I tell you F was wrong? I did not. Come on now. Sorry about that. I said I couldn't read your F. Oh well. So let's go through the basic components. If you have a source that is at TL and you're trying to pull heat out of it maximally, you want minimal or to no irreversibilities, then all of this QL is going to go into a system where the working fluid is all at TL. This is a key idea, that temperature in the working fluid inside of our system is all at TL. But professor, you're adding heat to it. How can you keep it at constant temperature? Phase change. And so what type of phase change would be happening if the fluid's coming in on this side, going out on that side? What type of phase change the fluid's undergoing? Is it condensing or evaporating in this device? I'm going to pause, walk around. I never said thermo was easy, did I? But hey, the fluid is evaporating. So should we call this heat exchanger an evaporator or a condenser? It's an evaporator. Why do they call that heat exchanger an evaporator? Because the fluid flowing through it evaporates. All right, and then it comes out and it goes over here to another heat exchanger. That heat exchanger over here is hooked up to, let me scoot this all down. I didn't start it there, scoot it all down. This is all hooked up to another high temperature reservoir, or temperature reservoir that's at high temperature. Which way is the heat being transferred between the working fluid and the heat exchanger? It's coming out. Maybe you put a Q dot H just like this, maybe as a Q dot L. All right. So now, if the fluid was evaporating in the evaporator down below, what is it doing in this other? Condensing. But hold it. It's exposed to a high temperature heat sink, right? It's backwards, but that's the right way. It really is. It's at high temperature and it's condensing. This is the miracle and the wonder and the difficulty of refrigeration. So, can I have it such that the fluid comes in at TH and goes out at TH? And yet there was a lot of transfer out of the fluid, a lot of heat transfer. Yeah, and that's the phase change. It's the condensing. So what do we have in between? Well, we recall our PT diagram, which is a projection of the PVT surface. And we recall that we had a region up to a point, then a line up to a point, a line up like this. And then what was the name of that point? And what was the name of that point? The CP and the TP. CP for critical point. This is actually the dome. Look sideways at the dome, the projection, the PT projection of the PVT surface. And this is our triple point, or triple line, but a line looks like a point when you have the right projection looking at it. So up in here is a sequence of single phase, which is liquids. Down here is a region of single phase known as vapors. And guess what's over here? Solids. Think of this. Cold gives you solid. Hot gives you vapors. And if you have high pressures tend to give you solid liquid, and low pressures tend to give you vapors. Okay, so what's happening is think about the sequence of states right here. This is key. Such that if I want it to be changing phase, going from liquid to vapor, vapor to liquid, and I want it to happen at a relatively high temperature, TH, you come up, you go across. What do we know about that pressure? It's high. pH would be the pressure, saturation pressure at that temperature, TH. All right, what happens if I want to be in the evaporator? I want to be evaporating at relatively low temperature, the pressure of the working fluid, the refrigerant, in the evaporator, is it high pressure or low pressure? It's going to be low pressure. TL gives me P low, which is the saturation pressure at that low temperature. So the evaporator, low pressure. The condenser, high pressure. Okay, but what is the device then that's needed to go in between? It's a compressor. So what's the goal of the compressor? Feed work to boost the pressure. All right, and then what do we have over here? You need to drop the pressure, so we put a turbine. So those are the four components. So you have, that didn't spell turbine very well. Turbine, okay, so you have an evaporator, a compressor, a condenser, and a turbine. Which way does the fluid flow? In that direction. Why do we draw it like that? Because it's going to be lining up with the states on a TS diagram. So we typically will start the numbering 1, but there's nothing special about where you start numbering, but to be consistent with the textbook, 1 is what comes out of the evaporator, goes into the compressor, then it's followed by state 2, then followed by state 3, then it's followed by state 4. So everything's going to be tucked underneath, put it on a temperature entropy diagram, underneath the dome. Now, the dome for refrigerant may not be symmetric as the water was, steam. So I'm going to show it to you, and I'll show you a real one in a second. It'll be shaped maybe like this. What's this point? Critical point. All right, is that the same CP as that one? Yes, they're the same. Yeah, okay. So now, if you have it at a high pressure line, let me try and draw a high pressure line. Comes like this, comes across like that. That's our high pressure. And here's a low pressure line, goes across like that, and there's PL. And you want all of this heat to be into the fluid at constant temperature and out of the fluid at constant temperature. And so to fit the Carnot cycle, refrigeration cycle on this temperature entropy diagram, the best you can do is put state 2 right there, which state 2 is saturated vapor. It's at the corner. This is saturated vapor. And state 3, you tuck it way over here, state 3, and that's going to be saturated liquid. Now, you think about the perfect turbine. You're going to expand to go to low pressure. There's not going to be any irreversibility. There's not going to be any heat transfer in that turbine. So guess what's constant from state 3 to state 4? Is the pressure at 4 equal to the pressure at 3? Is the temperature at 4 equal to the temperature at 3? Is the specific volume at 4 equal to the specific volume at 3? Is the enthalpy at 4 equal to the enthalpy at 3? Is the internal energy at 4 equal to the internal energy at 3? Is the entropy at 4 equal to the entropy at 3? See what I'm getting at? The last one. Why didn't you just tell us that, Professor? Can you see what it is? Now, there's a lot of work that you went through to get that, but it's isentropic flow through that turbine. So where is it? State 4? Straight down. There's state 4. And then you do the same thing over here from 1 to 2. And there's state 1. What does the cycle look like? A rectangle tucked under the dome for the TS diagram. So let's solve this problem and flush it out. So we have refrigerant 134A. Might as well work with the refrigerant. And it's a Carnot refrigeration cycle. The evaporator temperature is 4 degrees C. Can you tell me what the evaporator pressure is just based on that we know that it's 4 degrees C? You go, you look up the PSAT at 4 degrees C. And if you look it up, it looks like it's a whopping 337.3 kilopascal. Somebody has an ice pick. They come up to that evaporator coil. They poke a hole in it when it's running and the pressure is 337.3 kilopascal. Does air rush in or does refrigerant rush out? It rushes out because atmospheric pressure is around 100 kilopascal. All right. The pressure, the saturated vapor enters the condenser at 52 degrees C, and saturated liquid exits the condenser at 52 degrees C. That's TH, 52 degrees C. What is the pressure in the condenser? Is it greater than the pressure in the evaporator? Yeah, it will be. And we look it up based on the data, and it's 1385.1 kilopascal. 13 or 14 bar around there. The mass flow rates given, m dot of 5 kilograms per minute, determine the rate of heat transfer to the refrigerant passing through the evaporator. That's part A. So the first thing you do is do a schematic, right? Then do the TS diagram, which we did and hopefully you have on your notes. What's the next thing you do in the strategy for solving for part A, B, C? Get a table of properties. Then the next one, table of transfers. Get the table of the Q's and the W's. All right, so I'll quickly try to resketch the components. This is the condenser, this is the evaporator, this is the compressor, this is the turbine, this is state 1, state 2, state 3, state 4. Let's go ahead and make. So we have our states, and we're going to have state 1, 2, 3, 4. It's Carnot, so I don't have to worry about efficiency for the compressor or efficiency for the turbine. It's all isentropic flow. So we're going to have pressure in kilopascal. You know, I can fill out those 4 pressures right away, because all I have is high pressure or low pressure. It's cut right in between. This is all the high pressure. State 2 and state 3 have the same pressure. That's the high pressure. Let's go ahead and fill that out. State 2 and state 3 is 1385.1 kilopascal, 1385.1 kilopascal. And then the pressure of 337.3 and 337.3. Now, let's talk about the temperature in degrees C. What about state 2 and state 3? What was that temperature? 52 degrees C. 52. What about 1 and 4? Yeah, 4 and 4. Now, we're going to use quality. We'll also use enthalpy, kilojoules per kilogram, and entropy, kilojoules per kilogram Kelvin. All right? So, 2 of those are pretty easy, because at state 2, it's saturated vapor, and state 3, it's saturated liquid, is it not? So the quality at state 2 is 1 and 0. So this will be H of G and S of G. And this will be H of F and S of F. How do I go between state 2 and state 3? You basically go, between 3 and 4. The S4 is equal to S3. It's isentropic. Now knowing S4, we can get the quality at 4, S4 minus S of F divided by SG minus S of F. Have you done enough of these? Yeah. And then you would get the quality. Then knowing the quality, you would get H4 is equal to HF plus the quality at 4, H of G minus H of F, or HFG, either one. You do the same thing here, that S1 is equal to S2, so you get then the quality at 1 and then the enthalpy at 1. Same process. Once I have those, I do a first law analysis around the compressor. Let me scroll down a little bit. I'm going to put a table of different components. I didn't leave enough room. And I want the Q in kilojoules per kilogram and the work in kilojoules per kilogram. All right? So the first component would be the compressor. Is there any heat transfer? Nope. And the work, I know that it's positive in, but we're going to stay with the right sign convention. And so it'll be H 1 minus H2, which will give me a negative W. Okay? And then the next component's condenser. Well, there's no work, in or out of the condenser. So if I do a first law analysis around the condenser, and I know that it is definitely heat is out, so it's going to be the H. It'll be a negative Q of the condenser because it's not in, it's out. It'll be H 3 minus H2. All right. What's the next one? The turbine. That one is out, so it'll be H3 minus H4, positive out, no work. No heat. And then the evaporator, there's no work, but we have the heat into is going to be H1 minus H4. And when you do the net, if you do the sum of the Q's, Q net, and work net, guess what? They need to equal. If they don't, you have an error. Look for your error. All right. Then you can answer the questions. So here is the solution. We just tucked a little information. Okay, there's the M dot. This is a table of properties. What do I put a little note out here? I say, oh, temperature and entropy help fix state 1. Temperature and entropy help fix state 2. It's temperature and saturated vapor, temperature and saturated liquid. Notice the qualities, it's around 37%, and no, that's 97%, and this is around 32% quality. Then this is a table of the transfers, and then the answer for what is the rate of heat transfer to the refrigerant passing through the evaporator, that's Q dot evap, if you like to do that, is the mass flow rate times Q evap, which we calculate right there. And so that comes in at 3 tons of refrigeration. How about for part B, the net power input to the cycle? So W dot net in is the mass flow rate times specific net in. Well, this will be a negative on there to turn it into an input, but it'll be negative 21.96 kilojoules per kilogram times the mass flow rate, make it a positive power in. And the coefficient of performance. So the COP for the refrigeration cycle, isn't it the answer for part A? Q dot evaporator, what I want, divided by what I have to supply, and you'll get 5.77. And I can check with this very simple equation using the absolute temperatures in Kelvin, and you get the same answer, which is a great confirmation. This is a drawn to scale temperature entropy diagram for refrigerant 134A. What were our temperatures for the condenser? 52. So it's around 52. Right there. So there's state 2, state 3. What was our temperature for the evaporator? Around 4. Right there is around 4. Come across. And then this is state 4. And this is state 1. You could tell that it's not as symmetric on a TS diagram. It's skewed over such that the quality at 1 was very high. What was it, 97 or 98%? And yet the quality at 4 was around 32%. Make sense? Why is the Carnot refrigeration cycle not practical? Because of this component. What's up with that compressor? We have a two-phase liquid mixture coming in. So what we do is we shift it, and coming out of the evaporator, it's saturated vapor. But you just changed it now, because once I have on a temperature entropy, maybe I go back here. Once I shift state 1 over here, and I compress it, state 2 is going to be a higher temperature. And now I'll have to de-superheat it to cool it off before it starts to condense. It'll come out of that compressor superheated vapor, which makes it okay, but it's not going to have the efficiency that the Carnot did. What's the other impracticality? Is that turbine, you really can't find a turbine that takes saturated liquid at high pressure, high temperature, and expands it to low pressure, that's okay, but low temperature, and it's still a two-phase mixture, saturated liquid to two-phase mixture, there's not one out there. So you just substitute for one of these. What did I just replace it with? Just expansion valve. It'll drop the pressure. The material, the refrigerant will flash coming through it. The pressure's a lot lower. The temperature will be really low coming out of that device. And that's the expansion valve. So when we come over here, if you have from state 3 to 4, 4 will be kicked over here, and it will be irreversible. There will be some entropy generation. Well, with that, I'm going to go ahead and stop and pass back your exams.